So let me just start off making a few quick announcements. So just about the test, so the midterm on Thursday. So it's going to be 10 true or false questions. And again, just your answer will be true or false, and then 5 very short answer. Each of these very short answer questions, by very short, I mean the answer is a positive integer. Okay, so just so you know what to expect, and you'll have 1 hour. So we'll start, I'll put the file on to the website. So you'll just get the PDF off the website, and so I'll upload it at 12:30 p.m. You'll be able to download it. And so someone just asked, do we need to justify our answers for the true false questions? No, you do not. So it'll be just, well, of course, for yourself, you should justify the answer, but for all of these, you'll only turn in your answers. So it'll just be just the word true or the word false for each of them. So I want to make the submission as simple as possible. So you'll have an hour to work on it, and then as much time as you need to upload. The idea is sort of you can work however you want on it, like on scratch paper or whatever, and do it all in your head, whatever you want. And then you can copy your answers down into like however you need to do it to get them into a PDF, whether you do it on a word processor or a tech, or you do it on a piece of paper and take pictures. You can do that after the hour is over, and then upload them to Gradescope. So just think in advance what's going to be easiest for you to do. Just like the homeworks, I'll post the PDF with the exam and the tech file. So if you want to just like put them into that tech file at the end and then upload that, that works. But also just whatever is going to be easiest for you to get the 15 answers into Gradescope. So everyone should come to the Zoom for this because, well, I'll put you into breakout rooms and you can call me and ask questions if you have any questions during the exam. And then afterwards, just stick around in the Zoom while you're uploading it, because then if you have any problems, we need to troubleshoot anything, we'll be able to figure out the upload. Are there any other questions about what the exam is going to look like in terms of just like literal logistics / structure? Okay, great. So that was the first announcement. Next announcement is well, I guess it wouldn't make sense for me to have office hours Thursday night tonight, so I'm going to move my office hours to tonight. Someone asked, is it okay to write answers on a tablet? Sure. Whatever, anything that works, anything that you can sort of then. I mean, the constraint is write your answers in a way that you can then upload them to Gradescope, or at least copy them down to something where you can upload them to Gradescope. So if you can do that with your tablet, that sounds great. Rebecca, did that answer your question? Okay, thanks. Okay, so yeah, so the office hours are going to be tonight, so Tuesday. At 8:30 p.m. to 10 p.m. So sorry, I should have announced that last week, but I'm not okay. But this way, if you have any questions before the exam, you can ask me. Okay, let's see, what else do I want to say? I guess let me make just announcements about what next week looks like. So next week. So next week is like the spring pause week. So class is optional, and we're not going to do anything new or anything. So on Tuesday, the 9th, we're going to we'll just go over the midterm. So, well, if anyone shows up, I'll just go over all of the answers to the midterm. And if no one shows up, then, well, I guess if no one shows up, I'll still record myself going over the answers to all the midterm problems. So, so we'll have that. And then on Thursday, 3/11, class will just be the office hours. So if you have questions about anything, just come in, and the office hours will not exist. So the regular office hours on Thursday evening next week will be canceled, and we'll just have the office hours of the class. And then the week after that, we'll get back to sort of the normal schedule. So things will look the same. All of this information about, so I just uploaded, or did I? Let me see if it went through. Sorry, I was having problems doing this right before. I think I just updated the website with all this information. Right, so the website, like if you scroll down to like the weekly handout / homework section, it has this information about what's going to happen the next 2 weeks too. So you can keep track of it there. Good. Any questions about that? Okay, great. So then let's talk a little bit about the content of the exam. So I'm going to pull up the syllabus of the class. So it might be helpful for all of you, right, to look at the syllabus of the class and just see what we've covered. So, okay, so first point, you guys are all sort of seasoned veterans of being students by now. So you can already deduce a lot of information about what will be on the exam just based on the structure and the fact that they're going to ask true false questions or questions that have a positive integer. Like, well, answer, like there are probably like only so many things I can ask about. You've done lots of problems that involve like counting things. You like know lots of things about counting things. I mean, the topic of group theory is particularly lended to sort of like the subject of finite group theory particularly lends itself to asking questions that have just a positive integer answer. So, but if you think about it, you can sort of go through and think about what are the kind of questions I could ask. Okay, so probably is a good exercise to sort of do that and look at the homework and see like, and you can look at what exercises I could be reinterpreted as like asking a similar exercise, but where you just give a positive integer answer. Okay, and so, right, so if you look in the course description, then copied from the graduate bulletin, there's a list of topics that we're supposed to cover in this class, and we've covered a good portion of them. So let me sort of just list those topics. So, so from the syllabus. / bulletin. We've done subgroups. Okay, well, I mean, there's not much there. Subgroups are sort of one of those things we just use all the time. And sort of knowing about subgroups is sort of built into anything else we do. It's not like there's something specific you need to study about some of the subgroups. Normal subgroups. Again, sort of on the, like this is a graduate class in algebra. I'm like not going to ask you to sort of define a normal subgroup or like prove by computation some subgroup is normal. So just know how to use, and somehow these topics, like a lot of the topics in this list, they're all like so basic and things you already knew before from your undergraduate algebra classes that they're sort of, they get built into, means, yeah, you don't have to sort of study them specifically, they're sort of built into the more advanced things. But let me just keep listing them. Quotient groups, same idea. Homomorphisms, again, this is part of the very basic structure we use all the time. Isomorphism theorems. Well, I think you guys all know already how I feel about isomorphism theorems. I mean, of course, I'm not going to ask you to like, well, given the structure of the test, I couldn't ask you to sort of state an isomorphism theorem. I mean, technically, I've told you that there are going to be 5 very short answer questions where the answer is a positive integer. So if I was like really mean, I could like state a theorem and then ask you like which number isomorphism theorem this is. But of course, I'm not going to do that because I don't care. I don't care if you know the names. Like I don't care if you know the numbers of isomorphism theorems. And I don't care if you know the statements. Like all I care is if you know how to use the statements. In the sense that you should know the ideas that are expressed in the isomorphism theorems, and you should know like the statements are true. You don't have to remember like which isomorphism theorem to cite to do it. But so in maybe the isomorphism theorems, like they could show up as a tool you use in like one of your computations, but like you don't need to. They're tools you should know how to use. Like they're not things you need to memorize. Okay, then groups acting on sets. Okay, well, of course, you should know the definition of a group action, know like all the standard examples we've thought about. Orbits. So you should know. So now we're sort of starting to get into something where like, well, like these are questions I could actually ask. I could ask you like, how big is an orbit of some group action, or like how many orbits are there for some group action? So this is sort of starting to be something that could actually show up on this kind of exam, like directly. So I make sure you can answer that kind of question. You know, sort of basic examples. So like in things we've thought about before for group actions, like we've thought about like symmetric group action acting on sort of the set from 1 to n just by permutations. We've thought about like the action of groups on cosets or on conjugacy classes. We thought about like the actual dihedral group on like the vertices and edges of squares. We thought about or higher n-gons. We've thought about the action of like GLN of a field on like column vectors and so on. And know like the sort of examples of group actions and sort of in how and what are orbits and stabilizers that we've looked at in this context. And that's the kind of thing that could sort of show up in a computation or a question that has sort of a numeric answer. Okay, so orbit stabilizers, the orbit decomposition formula. I don't know what that means. I guess that probably means, that must mean sort of this theorem that sort of every orbit is sort of G mod H for H the stabilizer of some element in it. And you can write any G set as a disjoint union of the orbits. So it's sort of the structure theorem for G sets. And that's sort of built into like, okay, I keep on saying this, so you can sort of deduce, because I don't have a good poker face and I'm not good at obscuring information, you can sort of deduce from how many times I've said that you should be able to count orbits, that there's going to be a question about counting orbits on here. And sort of, well, I mean, this is related to that, of course, the fact that any group action breaks down to its orbits. Okay, Lagrange's theorem, again, that's sort of just a basic tool that and you already know from undergraduate algebra. It could show up in a computation, but I doubt anyone has to review Lagrange's theorem at this point. You might have to review the name because I always forget that it's called Lagrange's theorem, but surely you know the statement that the order of a subgroup divides the order of the group. I mean, I literally like the first time like when I was writing the syllabus for this class and copying this list of topics from the graduate bulletin, I was like, I saw the name Lagrange's theorem. I was like, what's Lagrange's theorem? And I had to look up what Lagrange's theorem was because I couldn't remember. Well, I didn't know the name of it. Okay, you guys already know I'm bad with names of theorems and stuff. But anyway, it doesn't, yeah, you guys know the statement and that's what's important. Again, you don't need to know it's called Lagrange's theorem. You just need to know the order of a subgroup divides the order of a group. Like in the context of this class, this was sort of the first example we saw of like the utility of looking at group actions. So it might be useful to like go review that and remember that, like how you prove Lagrange's theorem. Though again, of course, I can't ask you to prove something and then write an integer that a positive integer that encodes your proof. So you don't have to worry about being asked to prove it on the exam. Okay, and then Cayley's theorem. Okay, so this one I remembered when I put it on the syllabus, when I copied it onto the syllabus. So it took me a second. So this is this completely useless statement that every group embeds inside of, like every finite group embeds inside of a symmetric group. I mean, not completely useless, but essentially useless because like it's only like that's only a useful statement somehow if you have it done in an interesting way. Like the way you prove Cayley's theorem is you just consider like the action by left multiplication on the group itself. I'm like, well, okay, sure, that gives you Cayley's theorem, but like it doesn't give it to you in a useful way. So what's more interesting than Cayley's theorem is like thinking about like sort of back in the context of groups acting on sets, like thinking about, well, whenever you have a faithful action, like that gives you an embedding of your group inside of a symmetric group. So, well, Cayley's theorem is sort of useless because you just embed your group in some gigantic symmetric group. But like often in examples we've seen, like you can embed your group in some much smaller symmetric group, and that's sort of an interesting thing to do. Although then we also saw an example where you couldn't embed it in a smaller symmetric group. So and sometimes Cayley's theorem is sort of optimal. So for example, the quaternion group Q8 doesn't have a faithful permutation representation of size less than 8. You might go back and review that statement. So actually, and I should sort of put this somewhere on the side. And so I already mentioned sort of examples of group actions, but you should just go through and make sure you know sort of the basic groups we've talked about. So symmetric groups, alternating groups, dihedral groups, like general linear groups over fields, especially over finite fields, like over like FP. I mean, like the quaternion group showed up in a couple of examples. This group of 8 elements, that's one to be in your head. I probably already said dihedral groups, abelian groups, finite abelian groups, especially like basic semi-direct products, sort of all these examples of groups that we've worked with. You want them to be fresh in your head because, of course, like again, so you can backwards engineer what I can ask about, and if all I can ask is like true or false or numeric answers, you can bet like there are going to be some explicit groups showing up where you have to do some computation with those explicit groups. So it'll be helpful to have sort of those like the groups we've covered in your head and fresh in your head, so you don't have to sort of refresh the structure. Okay, so yeah, so Cayley's theorem was on here, but sorry, and then I went on a rant, but the point was you don't need to know Cayley's theorem for this exam, but you should sort of like it will be helpful to like maybe it'll be helpful to think about the fact that when you have a faithful permutation representation that gives you an embedding group into SN, and just thinking about related examples like that will probably be useful. Okay, C-loss theorems. Well, that's a no-brainer. I mean, probably over half of the problems on the exam will need you to use C-loss theorem. Probably maybe not over half, but probably so 1/3 to 1/2 of the problems on the exam will need you to use C-loss theorem in some way because, like we spent a lot of time using C-loss theorem to like deduce various results about groups. So but that's okay. And like probably you don't need to review anything if you've been doing the homework either, because by now the C-loss theorem should be sort of embedded in your head if they weren't already before the class. Permutation groups. Okay, I already said that, but in the context of the syllabus, this means symmetric groups and alternating groups. Or does it? Because the next thing in the syllabus is symmetric and alternating groups. Okay, well, you can interpret the graduate bulletin how you will. Simplicity of AN. Well, okay, symmetric multivating groups are very specific examples of groups. So of course they could show up on the exam. We spent lots of time talking about them and their structure of these groups. So aspects of their structure could show up on the exam. And a big portion of the class so far has been talking about simple groups. So you can expect that there will be some questions about like, especially like existence or non-existence of simple groups. And this is the kind of thing that has like a true or false answer. So it's sort of a natural question. And well, so you should know all of the examples of simple groups we've discussed. So here's simplicity, and the alternating group is sort of this biggest example. We also looked at like GL3 over F2 in the class one day, and we saw that with a simple group. And so yeah, and simple groups were a big theme. A lot of what we did was about showing simple groups don't exist, but we also talked about simple groups that do exist. So of course, make sure you know which simple, know something about the simple groups we've discussed. So in particular, the alternating group for n greater than or equal to 5 was like the biggest example we discussed. Okay. Direct and semi-direct products. I mean, again, this is one of those, and they're just a basic tool you should know how to use. I mean, so semi-direct and semi-direct products in particular like showed up when we were classifying groups. So like I had like a completely reasonable question would be like for me to pick some small number, like maybe a product of 2 primes, and ask you how many groups there are of that order. And so like that you'd sort of have to understand something about semi-direct products, and okay, so you should sort of understand that much, like really how you use them. Like a true or false question, I could ask like, can you represent this group as like a here's some group, can you represent it as a semi-direct product? Like this is, I'm not saying I will ask this, but and this is, and you can imagine sort of true or false and recounting questions that involve semi-direct products. But again, it's just, they're really a tool that you use in computations or in sort of understanding the structure of things. So know how we've used these tools and how to use these tools. Okay. Exact and split exact sequences. Okay, and this is just basically some finer points about semi-direct products. It showed up on a homework assignment, on a homework question. Well, I'm not going to, I'll just say I'm not going to ask a test problem that says the word exact and split exact or split exact sequence. So this sort of won't show up on the midterm, but because there's only the one homework problem about it and sort of a side issue. And you should know it, and you should know sort of how this fits in the context of semi-direct products. But okay, so there's a freebie. There's not going to be a question. It says like true or false, the sequence is split. Okay, commutator subgroups. Solvable groups, nilpotent groups. So all this stuff we talked about pretty recently. And know what it means to be solvable, know how you check it. And you should maybe think about the basics, you should think about the examples of, okay, earlier I sort of was talking about some examples of groups, and like in the classes on solvable groups, like we talked about examples of groups and we talked about which ones were solvable and nilpotent, and like this is something maybe worth thinking about before the exam is like of all like the basic examples of groups we know, like which ones are solvable, which ones are nilpotent, and so on. Like that's sort of a natural thing to ask about. I didn't write this down, and this is not in the, and so it's sort of built into these things is also like the derived series, the lower central series, the upper central series. There's not a question where I'm going to ask you like how long is the upper central series, or like how long is the derived series for a group, but like I could ask you whether a group is solvable or nilpotent. Well, okay, I'm not going to ask you whether a group is nilpotent because I already said we don't like, that's not so important for us. But I could ask you whether a group is solvable. So I know the basic computations for this. Okay. Solvability of P groups. So we sort of talked about the fact in class that groups of order p squared are abelian, and then you had a homework problem where you showed that groups of order a power of p are solvable. This is an important basic fact. And it's even stronger in that they're not just solvable, they're nilpotent. So groups of order a power of p are nilpotent. Okay, but good. So you should know this. In the classical matrix groups, so we haven't spent so much time talking about things. We've talked about GLN, we've talked about SLN. I think briefly in some lectures I might have mentioned the orthogonal group and the symplectic group. But we're not. I won't ask a question about the orthogonal or symplectic group. But you can expect to see at least GL2 or SL2 showing up when we've done sort of lots of examples of these kinds of things, or PSL2. So those are things you should know. And again, because I'm asking counting problems, you could sort of maybe expect that it's more likely that GL2 of a finite field rather than GL2 of R is going to show up, because sort of it's a little easier to write down counting questions about a finite group than an infinite group. Okay, automorphism groups. In the meantime, we talked about automorphism groups in class. Well, and if you sort of, depending on which problems you did, you might have done a couple of problems about automorphism groups. But in class, the main time automorphism groups showed up was in the context of semi-direct products. So sort of if you're comfortable with semi-direct products and sort of how automorphism groups appear there, then this is sort of based on what I taught, it would be unreasonable for me to really demand more. Jordan-Holder theorem. Okay, and this is just something I stated and it's of philosophical importance, but no practical importance for us. So I think you know how I feel about it. Certainly won't be on the exam, but you should know it. Free groups. Free groups are really important, but the emphasis has been on finite group theory, and so free groups are not going to show up on this exam. And presentations of groups. So let's cross those ones off. Those won't be on the exam because other than introducing them and just sort of recalling them at the start of the class, we haven't really done anything with them. And to be honest, presentations of groups are not occasionally they're very useful, but for nothing they haven't been useful for anything we've done. So, for everything we've done so far, introducing a presentation of a group would have made it more work rather than less work. If you thought about sort of the dihedral group in terms of this presentation instead of just sort of, I don't know. Okay, anyway, it is what it is. We're not going to do so much with them. I'm not trying to dismiss free groups and presentations groups as useless, as not interesting things. Just they show up in sort of different applications of group theory than the ones we're discussing in this class. So, for example, free groups and presentations, they're very important in algebraic topology. So if you're studying fundamental groups of surfaces, fundamental groups of higher dimensional manifolds, they show up in all sorts of ways, and it can be very helpful to have a presentation. The idea of whether you're finitely presented or not is important in all areas of mathematics, but maybe the explicit presentation is not always so important. So these are important topics. These are important topics, but sort of more so when you're doing applications of group theory that involve infinite groups. And for the most part, this class is focused on applications of group theory that only involve finite groups. And then these ideas are, well, it's not so surprising that they're less immediately applicable. So, okay, so there won't be a question about free groups or presentations of groups on this exam. And okay, so those are all the topics in the graduate bulletin that were then copied into the syllabus about group theory. And so just to summarize, and then this is basically what, and these are the things we've talked about so far in the class. So, I mean, this first set of stuff sort of all just things that, like, basic structural ideas that you should sort of have on the back, like, and you don't have any problem with anymore. So it's not like you could study anything with them, even if you wanted to. In orbit stabilizers, orbit decomposition formula, like, easy to think about lots of questions you could ask with numerics there. So think about that, review that, like review related problems we've done. Lagrange's theorem, Cayley's theorem, and they're just basic structural results that you know, and Cayley's theorem is useless, and Lagrange's theorem, well, you know, it sort of fits one of those things you know by heart. The C-law theorems, like by now you probably know them by heart as well, and you know, right, we've used them in everything since we introduced them. So good. All the examples of groups, examples of simple groups, structure, like solvable groups. So the groups built out of abelian groups, and all the examples we've seen of that, like P groups, GLN, finite fields. Yeah, okay, good. So those are the things that will be, like, that's, I know, okay, so this was some impressionistic summary based on a list of things that gave you some impression of what will be on the exam, and where I didn't write everything down, but you could always, this is taped, so you can always go back and look at this like 5-minute diatribe if you need to extract any more information about it. Are there any questions about any of these topics? Or anything in the class? Okay, great. Well, I think maybe we'll just stop there then. Oh yeah, okay, please. No, it could be as long of a question as you want. Yeah. Okay, let me pull it up. So, okay, so it's week 4. Exercise for problem 1, or part 1. That's right? Okay, and so, right, so the idea was, suppose, well, I'll just copy the problem statement down. So suppose K is a cyclic group. So that could be Z mod NZ for some N, or it could be just Z itself. So it could be an infinite cyclic group. And the phi, so you have 2 maps from K to automorphisms of some group H. So H is just some group. And then, so the hypothesis is, suppose the subgroups phi1 of K and phi2 of K are conjugate in the automorphisms group. And then there was this little parentheses which says, if K is infinite, then assume both maps are injective. So, and then you want to construct an explicit isomorphism from H semidirect phi1 K to H semidirect phi2 of K. Okay, and so then the question was, where are you using, like, why do you have to make this special assumption when K is infinite? So let me just point out, I mean, so if K is not infinite, so K is equal to Z mod NZ, then, well, here, and there are different ways you can think about this, but one way to think about sort of the main properties going on here, let me say it this way. Well, let me say it this way. So if K is finite, then sort of the size of phi1 of K determines the kernel. So the size of the image determines the kernel of the map. But this is not true if K is infinite. Because so when K is finite, the size of the image is just sort of the size of the group divided by the size of the kernel. So the size of the kernel is, so the kernel of phi I is equal to the size of K divided by the image of phi I. So that's the size of the kernel, but then so that's the size of the kernel, and then but K is cyclic, so there's a unique subgroup of any order dividing the order of K. Whereas in I mean, if oh, sorry. I think I'm saying the opposite thing. Oh no, I'm not. This is I'm sorry. Okay. So this statement is still going to be true. Okay. Well, everything I said so far is true, but it's not the important thing. So let me back up and start over. Sorry about that. So let me just give, instead of trying to say what's important, let me just give an example that sort of illustrates this. Sorry. Okay. So let me look at Z goes to, let me look at two maps from Z to Z mod 5Z. So two surjections. So I'm going to send 1 maps to 1. So this is going to be phi1. And I'm going to send 1 maps to 2. Okay, and so the image of both of these sorry, let me, So the image of both of these is just everything. But there's no way to, but the maps themselves are not conjugate by an automorphism of Z. So let me say it in, the maps are not conjugate by automorphisms by elements of Z mod 5Z or Z. So, and the point is, so like say like Z mod 5Z was the automorphism group of some other group. And okay, so this, so maybe I should pick an example where this was actually the case. So let me do same thing, but I'll do Z mod 6Z. Let me do it. So if I do Z mod 6Z, no, that's not going to work. Let me do Z mod 11Z. Okay. So let me, yeah. Sorry, okay. This will actually, this was a Z mod 10Z. And the point is I'm trying to give you an actual example. So instead of like something that's illustrating some phenomena, but not like easy to see as an actual example. So this is the automorphisms of Z mod 11Z. So, and really this, so I can identify Z mod 10Z with Z mod 11Z cross. And in fact, let me sort of write it this way. So let me not to fix a basis. So let me say, we give two maps from Z to Z mod 11Z cross, which is the group of automorphisms of Z mod 11Z. Sorry, it took me a while to get there. So I'm going to look at the two maps. I'm going to look at phi1 and phi2. So phi1 is going to be, and so I'm going to give two surjections. So, and if I give the surjections, then they're going to satisfy the hypotheses of the theorem. And so what are the surjections? I'm going to send 1 to, I guess, is 2 a generator of this? So 2 squared is 4, 2 cubed is 8, 2, 4, 16, 32 is, yeah, okay, so 2 is a generator. And let me send 1 to, maybe hopefully 3 is also a generator. So so 3 squared is not 1. So what is 3 to the 5th? So we go 9, 27 is 5, 15 is 4. Oh, so this has order 5. 4 is maybe, 4 is probably good. Nope, 4 is 2 squared. That has order 5. This group is Z mod 10Z, so there are, yeah, how many there should be generated? So maybe 6, or maybe, sorry. So okay, so I'm illustrating the fact that it's finding a primitive root. So finding a generator of this group is like some difficult problem computationally. So I'm illustrating this by like, so it's 5 a generator of this group. So we take 5 squared, that's 24. So I have to start writing this, which is equal to 3. And I go to 15, which is equal to 4. So this is 5 cubed 4. I just need to check 5 to the 5th. So this is goes to 20, which is equal to 9. This goes to 45, which is equal to 1. Okay, that's order 5. No frets. I'll take, let's go, 6 squared is equal to 36, 3. Oh, that's going to be good because, yeah, okay, good. So if I start with a generator, and I take -1 times it. So if I start with an element of order 5 and I take -1 times it, now I'm going to get an element of order 10. So, okay, anyway, so probably there are quicker ways to do it. These are two surjective maps. Both 2 and 6 are sort of generators of Z mod 11 Z cross. So these are both surjective maps. Sorry for dragging you through that computation in my head. Probably there were quicker ways to do that than what I did. Okay, so anyway, if we look at these two maps, like the point is there's no way to get from one of these to the other. Like there's no way, but by sort of the natural operations we have at hand in this problem. So, well, and of course we can't conjugate them. There's no way to conjugate them by some element of Z mod 11 Z cross in order to get them here. But there's also like, so we can't precompose with an automorphism of Z. To go from phi1 to go from phi1 to phi2. So that's the issue. So like, because precomposite, so and the only automorphism is Z, so Z is just plus or minus 1. Just the units in Z. So you can multiply, you can have the identity, or you can have multiplied by -1. And so, like, so let me sort of write. So phi1 composed with sort of multiplication by -1. Well, that's going to be the map that sends 1 to okay. So now we find the error in my example. To 2 inverse, which is equal to 6. So in fact, so it's okay. So this is equal to. Yeah, so let me compute this. So if I take phi1 and I precompose it with sort of multiplication by -1, then that's, and I sort of see where the generator 1 goes. And this is phi1 of -1, which is the inverse of 2 in Z mod 11 Z cross, which is actually equal to 6. So in fact, so what I was about to, so this was not true because exactly these do precompose. So phi1 -1 is equal to so phi1 composed with -1 is actually equal to phi2 in this case. So in this case, you can sort of use this fact that you can precompose phi1 with an automorphism to show the two semi-direct products are equal. So you can use this to show, so you can use it to show that the two semi-direct products. Okay, so this became an example. And like this is an important part of the problem. So when you're doing this problem for K for when K is a finite cyclic group, like you use the property. So if you basically use, like, once you know the images are conjugate subgroups, well, you can sort of just assume that first you can sort of compose with the conjugation to assume they're the same subgroup. But then once you have that they're same subgroup, you actually want to get to like the same map to that subgroup. In order to get to the same map of that subgroup, you use that sort of, you can move, like when K is a finite cyclic group, you can sort of move around, sort of, you have lots of automorphisms. Like you have sort of, if you're Z mod NZ, you have sort of Z mod NZ cross of automorphisms, and you can use that to move around to make the maps actually the same map. Okay, so the point is, in general, if you take Z here, like you have many fewer, like if you take Z instead of Z mod NZ, you have many fewer automorphisms to pre-compose with. And so you're not, like, even when you know the image subgroup is the same subgroup, you're not going to necessarily be able to then move around with this, like by pre-composing with this automorphism to get the same map. You will be if the map is injective, because if the map is injective, then like sort of the image, so if the map is injective, then the image subgroup only has two, like the image is just Z. And so that, like, that subgroup only has two possible generators, and sort of they're just given by the generators of the group you started with. So like when the map is injective, you can always sort of, like, when the map is injective, you like there's only sort of two possible maps once you know what the image is. Okay. But if otherwise, there are sort of possibly more possible maps that don't work. So let me try this again. I mean, so let's see if we can actually produce a counterexample. So, and how many primitive roots of unity are, like how many generators are there of phi of 10? So there should be 4 things in this subgroup, right? So this is the number of generators of Z mod 11Z cross, which is just isomorphic to Z mod 10Z. It's like phi of n is the number of generators of Z mod NC. Okay, and phi of 10 is 4. So I got unlucky because I picked the 2 generators that differed by, I picked 2 generators that differed by sort of multiplication by -1. But I bet, so I bet if I think about the computations I did, I can get something else. So let's try, so probably -3. So, okay, so let me just recall. Okay, well, you've sat with me so far, so we'll sit through the rest. So 3 in Z mod 11Z. This has order, there's the 3 squares equal to 9, goes to 27, which is 5 cubed, goes to 15, which is 4. So this has 15 goes to 4, it's 12, so it's 3 to 4, it's 1. Okay, so 3 to the 5th is equal to 1. So that means -3 in Z mod 11Z cross has order 10, because -1 has order 2 and 3 has order 5. So I take the product in an abelian group, I get something of order 10. So good. So then, so -3 has order 10, and this is equal to 8. So okay, so I should have taken, so phi1 sends 1 to 2, and phi2 sends the generator 1 to 8. And now if I did this choice, now there'd be no way, like even though the images are the same because they're both surjective maps, because 2 and 8 both generate Z mod 11 Z cross, there's no way to conjugate, like there's no way to precompose with an automorphism of Z that sends one of these to the other. So like this, and this is something you probably did when you were proving the like case where K was finite, is you use like once you matched up the same subgroups, then you sort of could actually match up the maps as well by sort of precomposing with an automorphism of Z mod, an automorphism of K. And so, but this step breaks down when K is infinite. So when you have Z instead of Z mod NZ as your cyclic group, unless the map is injective. Yeah. So, okay. Well, apologies for the convoluted path I took to get here. But does that adequately answer your question now? Yeah, no problem. Okay. Now you have the bonus. You've also seen that like the internal machinations of my head are like at least as convoluted, if not much more convoluted than sort of anything going on in your own heads. So, so this is being easily confused isn't something that goes away as you learn more math. You just learn more math. But maybe the positive corollary of that is like, if you're someone like me who is easily confused, you can still be a successful mathematician. That's the positive phrase in that. Maybe none of you are so easily confused as I am, but if you are, sort of don't worry, you can still be a mathematician. Are there any other questions about anything from past homeworks or the class or what have you? Okay, great. Well, now I think it's much more reasonable to end class early because now there's only 20 minutes left. So I will, yeah, so let's stop. You can go study for 20 minutes or whatever you'd like, or drink a coffee, enjoy, or go to sleep. I don't know, whatever you want. And I'll see you guys on Thursday. And well, I'll still stick around for a few minutes in case anyone has questions.